constructing the pipeline. Okay, in this first situation, they are talking about the network connecting the wellhead in the Gulf of Mexico to and inshore delivery points. Okay, so they just try to find what is the network. Yeah. Let's look into the second situation. Is they want to determine the shortest route between two cities in an existing network of roads. So in roads, they have in between two cities, okay, they have many roads. So they try to find what is the shortest road connecting between these two cities. Okay. The third one, determination of the maximum capacity in tons per year of a coal slurry pipeline network joining coal mines in Wyoming with power plants in Houston. Okay, so this one they want to determine what is the maximum capacity. Okay, let's look into the fourth one. Okay, determination of the time schedule, start and completion dates for the activities of a construction project. And the third one, the last one, determination of the minimum cost flow schedule from oil field to refineries through a pipeline network. So the fourth one is they want to determine the time schedule. The fifth one is the minimum cost flow. So in these five situations, okay, we try to find what is the solution, okay, of this situation. Okay, so for the first situation, we can use the minimal spanning tree, okay, because in this situation, they just want to find what is the network. Okay, so for the second one, okay, they want to find the shortest route right between two cities. So we can use shortest route algorithm. Okay, and the third situation, okay, they want to find what is the maximum capacity. Okay, so we can use maximum flow algorithm. And the fourth one here is determination of time schedule. So we can use critical path method CPM algorithm. Okay. In this lecture, we will only discuss these two situations. Okay, we try to find what is the minimal spanning tree and the shortest route algorithm. Okay, so that we can solve some problems in OR. Okay, so let's look into the definition of network. A network consists of a set of nodes linked by arc or branches. So let's look into this figure. Okay, we have 1, 2, 3, 4, 5 here. Is the nodes. Okay, is our nodes. Okay, and the line here. Okay, the line here is for the arc or branches, which connect between one node to the others. Okay. The notation for describing a network is in bracket N, A, where N is the set of nodes and A is the set of arcs. Okay, and as an illustration, the network in figure 6.1 is described as this one. Okay, so N here is our set of nodes. So we have 5 nodes. So the set will be 1, 2, 3, 4, 5. Okay. A here is the set of arcs. Okay, so in this set, we will have several set of arcs. Okay, so we have the first arc. Okay, connect between the first node into the second. Okay, so we have 1, 2. Okay, the second one is 1, 3. Connect between node 1 to node 3. Okay, the third one 2, 3. Okay, connect 2 to 3. 2, 5 between node 2 to node 5. Okay, node 3 to node 4. Okay, node 3 to node 5. Node 4 to node 2 and node 4 to node 5. Okay, it's very easy. So you just need to remember what is our N. Okay, N is the set of nodes and A is the set of arc. Okay, let's look into this one. Okay, so we have several situation here. Okay, from our a network. Okay, we can get our path, we can get the circle, the tree, and the spanning tree. Okay. From this network, okay, we can identify what is the tree. Okay, the tree is a circle pre-connected, a network comprised of a subset of all the nodes. Okay, so if you look into uh, this this figure, okay, our network, okay, we can get the tree. So it will be 2, 1, and 3. So it will be a tree. One node with two branches. And this one is the spanning tree. Okay, a spanning tree links all the nodes of the network. So we have 5 nodes. Okay, with this 1, 2, 3, 4 arc, we can join these all nodes. Okay. A path here is a set of arcs joining two distinct nodes passing through other nodes in the network. Okay, for example, okay, the path is arc 1, 2, 2, 3, 3, 4, and 4, 5. Okay, from a path between 1 and 5. So from 1 to 5, okay, we can get from 1 to 2, 2 to 3, 3 to 4, and 4 to 5. Okay, so a pipe is they want to connect between the first node to the last node. So we can use this part lah. 1, 2, 2, 3, 3, 4, and 4, 5. Okay. Okay, let's look into the last one. A path forms a circle or a loop if it connects a node back to itself through other nodes. Okay, so a circle or loop, okay, is yeah, the circle. Okay, we can get the circle, okay, from 2, 3, okay, 2, 3, 3, 4, and 4, 2. Okay, if it starts from 2, it will get back to node 2. Okay, so this is the circle. Okay. Or we can say the loop. So any questions so far? Okay, I think that's easy. We can continue to example 6.11. Okay, this example we just try to learn how the network is actually designed. Okay, so we just read. Okay, the Prussian city of Königsberg, now Kaliningrad in Russia, was found in 1254 on the banks of river Pergel with 7 bridges connecting its 4 sections, labeled A, B, C, and D, as shown in figure 6.3. So we have these bridges, okay, and it's connect between A, B, C, and D. Okay, this is the area, and here is the bridge. Okay, so let's continue. A question was raised as to whether a round trip could be constructed to visit all the 4 sections of the city, crossing each bridge exactly once. Okay, a section could be visited multiple times if necessary. So in the mid-18th century, the famed mathematician Leonhard Euler developed a special part construction argument to prove that it was impossible to construct such a trip. Later, in the early 19th century, the same problem was solved by representing the situation as a network with nodes representing the section and the distinct arcs representing the bridge, as shown in figure 6.4. So, okay, the situation is they want to, yeah, boleh ke tu? Okay, the situation is okay. They have four sections A, B, C, and D, and they want to connect this section through the bridge. Okay, so from section A, they want to go to section B. They can use this bridge, and also they can use this bridge, right? Okay, and to section C, okay, from A can use this bridge and also this bridge. And from A to D, they can go straight, okay, using this bridge. Okay. So the last one is section D. Okay, so from D, they can go to B from this bridge. Sorry. And the last one, okay, they can go to C by using this bridge. Okay, D to C. So from this real phenomena, okay, they can get a network representing of Königsberg problem as this one. So this is section A, section B, section C, section D. Okay, they connect the bridge, okay, using this arc. Okay, so it can be representing as this one. So now we try to find, okay, the solution of network. Okay. The first one, we can use the minimal spanning tree algorithm. Okay, let's look into the definition first. Okay, the minimal spanning tree links the nodes of a network using the smallest total length of connecting branches. A typical application occurs in the pavement of roads linking towns either directly or passing through other towns. The minimal spanning tree solution provides the most economical design of the road system. Okay. So let's look into the algorithm. This is the minimal spanning tree algorithm. Let's N be the set, okay, from node 1 to N, okay, be the set of nodes of the network, and define Ck is the set of nodes that have been permanently connected at iteration k. So Ck here, k is the iteration. And we also have C bar k, which is the set of nodes as yet to be connected permanently after the iteration k. Yes, so we have the permanent one and the second one is not permanent. Okay. The following steps describe the minimal spanning tree algorithm. So we have only two steps. Okay. The first step is we set the C node. Okay. The node here 0 represent iteration 0. So this is our starting point. So we let the C node equal to none. Okay, symbol representing as nothing lah. Okay, and C bar node is n. Okay. N here is the total nodes. Okay, the set of all nodes. Okay. Now we go to step 1. Okay. Start with any nodes I in the unconnected set C node bar and set C1 equal to set I. Rendering the C1 bar is equal to n minus set I, then we set k equal to 2. Okay, k2 is the second iteration. C1 here represent the first iteration. Okay, C1 is the first iteration. C bar 1 is the first iteration. So if we have C1 is the set of I, the C1 bar will be n, the total nodes, okay, minus the I. Okay, so let's look for an example. In this example 6.21, Midwest TV Cable Company is providing cable service to 5 new housing developments. The figure here, 6.5, depicts possible TV connections to the 5 areas with cable miles affixed on each arc. Okay, the goal is to determine the most economical cable network. Okay, so they have here 6 nodes. Okay, they have the first one here. Okay, and they want to connect to 5 other areas. Okay, so here is the cable. The numbers here, okay, 1, 4, 6, 9, 3 is represent the months, okay, the length. Okay, so now we try to figure out the minimal spanning tree for this problem. So let's get back to our algorithm. Okay, we first set our C naught is this symbol nothing, and C naught bar is our n. So in this example, we can just write C naught is equal to this symbol, and our C naught bar is equal to a set, okay, from 1, 2, 3, 4, 5, 6, okay, because we have 6 nodes. Okay, so now we try to get into our first iteration. So in the first iteration, okay, we start from the first node here. So our C1 will be node 1, okay, the set of 1. Okay. And C1 bar here is 2, 3, 4, 5, and 6. Okay. If you remember, okay, so our C1 will be n minus I. If we set our C1 is set of 1, okay, the first node. Okay, so our C1 bar will be 2, 3, 4, 5, and 6. Okay, and then, okay, we need to draw a line, okay, connecting the first node into the other's node. Okay, but we need to look back into our example. Okay, for example, from node 1, we can connect into node 2, node 5, node 3, node 4. But we cannot directly connect this node 1 to node 6, right? So that's why here we don't have the line between node 1 into node 6. Yeah. Then we just need to write back the minds, okay, 1, 9, 5, and 6. Okay. So from this first iteration, we can determine what is the shortest route. Okay. So the shortest route here, the shortest link. Okay. So the shortest link here is 1. Okay, because 1 here is the smallest in between these 4 lines. Okay, between 4 arc. Okay, between 4 arc. So we set this as our our shortest link. Sorry. Okay. So from here we can get into the second iteration. We already connect this the first node into the second. Okay, because we find this is the shortest. Okay, now we need to connect, okay, between this node 2 into the others node. Okay, so our C2 now will be set of 1 and 2, and our C2 bar will be 3, 4, 5, and 6. Okay, a set of 3, 4, 5, and 6. Okay, because we already know the nodes. We need to look back into this figure. From node 2, we can connect to 5, connect to 3, and we connect to 4. So that's why we have this line. This arc. Okay, 2 to 5 is 3, 2 to 3 is 6, and 2 to 4 is 4. Okay. So in between these 3 arc, okay, we find this uh, between node 2 and node 5. Okay, the 3 miles is our next permanent connection. Yeah, I'm really sorry, I forgot to mention about the permanent connected. Okay, so these 2 and 5 will be our permanent connected. Okay, so here we already have 1, 2, and 5 is already connected. now we have C3 bar is 3, 4, and 6. So we only have 3 knots left. Okay. So from here, okay, our last point here is 5. We can connect to 4. Okay, besides we can only connect to 4. We want to, sorry. Okay, we connect to 4. We don't connect back into 1, okay, because we already connect it in the first iteration. Okay, so from here we find again what is our shortest link. So we get this 2, 4 is the shortest one. So in the fourth iteration, our C4 will be 1, 2, 4, and 5. Okay, so we only have C bar 4, okay, not 3 and not 6. Then we connect again, okay, in between is not 3 and not 6, okay, and we try to determine what is the shortest link. So we find this in between not 4 and not 6 is the shortest one. So it will be our permanent connection. The last one, we only have this knot 3 left, okay, so we will get like this one alternately, okay, it connects 5, 5, so 5, 5, okay. Let's look into this one again. Okay, this knot 3 is the only knots left. Okay, but to connect into these 3, okay, they got two options. Okay, but two option, the the distance is the same. Okay, is 5 and 5 miles. So that's why it's shown as alternate links. Okay. So this one, okay, is called as minimal spanning tree. Okay, and this one is actually the final solution lah. Any question before we go to the next part? Okay, I hope that's clear. We just need to connect, okay, the knot one into the other's knot and find what is our shortest link. Then we try to connect, okay, the knot one to the shortest to the next knot with which have the shortest link, okay, until we connect all the 6 knots. Okay, and let's look into the second example, the third example, sorry, example 6.31, equipment replacement. Renca is developing a replacement policy for its car fleet over a 4-year planning horizon. Okay. At the start of each year, a car is either replaced or kept in for an extra year. A car must be in service for from 1 to 3 years. A car must be in service from 1 to 3 years. The following table provides the replacement cost as a function of the year of a car must acquired and the number of years in operation. Hmm, saya terbalik lah. Sekejap ya. Okay, so this is the table. Okay, so in this table, they have equipment acquired uh, at start of year, okay, 1, 2, 3, and 4. and we also have replacement cost for given year in operation. So from this example, okay, we can draw our network, okay, to be like this one. So from 1 to 2, it will be 4,000, okay, because 1 sekejap. Okay, so they they represent the equipment replacement model as shortest route problem as this one. So from this given table, okay, we can draw the node to be 1, 2, 3, 4, and 5. Okay. So it will connect between node 1 into node 2. Okay, 1 and 1 here is 4,000. So we can write from node 1 to node 2, 4,000. Then we get into 1 into 3 is 5,400 here. And the third one is from node 1 into node 4. So it will be 9,800. Okay, this one. Okay, let's look into the second year. The second node here. Okay, from this second node into the next one. Okay, we will have 4,300. Okay, the second node into the fourth node, it will be 6,200. From second node into the fifth node here is 8,700. Okay. So from node 3 here, we can get into the fourth node, the node 4, 4,800. Okay, the second one here, it will be 7,100. Lastly, we have node 4 to node 5 is 4,900. Okay, so from this situation, okay, we can represent as our model. And saya rasa saya ada software yang benda ni kejap ya. Saya tak termasukkan dia punya solution lah. Sekejap ya. Okay, saya rasa saya ada solve tau sendiri punya, tapi tak ada pula. Jadi kita ikut solution yang daripada Taha ya. Sebab di Taha tu dia guna software, dia gunakan Tora. Okay, they use Tora to solve to find what is the shortest route. Okay, so here the bold arc, okay, yang gelap sikit ni adalah represent the solution. So the shortest route, okay, for this problem, it will be from node 1 to node 3, then node 3 to the node 5. And the total amount, okay, for replacement cost, okay, we just need to sum up is 5,400 and 7,100. So the solution will be 12,500. Okay, so that's it lah. Okay. We find the shortest route, then we just sum up, so that is the final solution. Okay, but I will try to give you the solution, okay, when I found, okay, but later lah, okay, I try to give you the solution for this one. Okay, but from book, okay, it just said that the shortest route is from node 1 to node 3 and node 3 to node 5. So let's look into the final subtopic, okay. The subtopic is shortest route algorithm. This section presents two algorithms for solving both cyclic, for example, containing loops, and a cyclic network. Okay. So the first one is this. Saya lupa kasih letak dia punya. Sekejap ya. Dijkstra. Okay. Yes, this one is Dijkstra algorithm. Okay, for determining the shortest route between the source node and every other node in the network. Okay, the second one is Wright algorithms for yes, Huanjun. Do you have any question? Okay, we just continue. If you have any question, don't be shy lah to ask. Okay, do not hesitate to ask. You can ask me at any time. So the second algorithm is Wright's algorithm for determining the shortest route between any two nodes in the network. Okay. Essentially, Wright's algorithm subsumes Dijkstra. Okay, it subsumes Dijkstra's. Okay, but for this lecture, we only discuss the Dijkstra algorithm. Okay, it will come out during your final, so please pay attention. Okay. This is Dijkstra algorithm. Okay, let Ui be the shortest distance from source node 1 to node I, and define Dij is greater or equal to 0 as the length of arc Ij. Okay. The algorithm defines the label for an immediately succeeding node j as Uji, okay, the cross bracket, equal to cross bracket Ui plus Dij, comma I. Okay. I here is not I, okay, and Dij is greater or equal to 0. Okay, we will use this formula later. Okay, don't worry. Okay, the label for the starting node, it will be 0 and dash. Okay, this is constant lah. Okay, our starting nodes will be this one. Okay, indicating that the node has no predecessor. Tiada pendahulu. Okay. So it will be our starting lah. Node labels in Dijkstra algorithm of two types. Okay, we have temporary and permanent. A temporary label at a node is modified if a shorter route to be node can be found. Okay. Otherwise, the temporary status is changed to permanent. So, in this algorithm, okay, we have these two types, okay, the temporary and permanent. Okay, but the temporary status can change into the permanent when we get our shortest route. Okay, and we have the steps here. Okay, but I think I don't have to explain this one. I will explain in the example lah. Okay, we'll just step check ya. Step 0. Yeah, this is not an error. Okay, it only have step 0. Okay, they don't have any other steps. So this is the only steps that have in the extra algorithm. Let's look into this example. Okay, example 6.3-4. Okay, a network in figure 6.11 here gives the permissible routes and their lengths in miles between city 1, which is our node 1, okay, and 4 other cities. So 4 other cities here, 2, 3, 4, and 5. Determine the shortest route between city 1 and each of the remaining 4 cities. So this problem, okay, we try to solve using the Dijkstra shortest route algorithm. So in the first iteration, okay, we assign the permanent level 0 dash, okay, the close interval to node 1. Okay, so we have node 1 here is 0 and 1. Okay, sorry. In Dijkstra algorithm, we use this a table like this one. Okay, so it will be like this one and this one. So in the first iteration, okay, node 2 and 3 can be reached from the last permanent level node 1. Thus, the list of level nodes temporary and permanent become this one. Okay, so the node 1 will be our permanent. The next node 2 and 3 will be our temporary. Okay, node 2 and 3 can be reached from. Okay, we start from node 1. Okay. From this node 1, we can reach node 2 and node 3, but we cannot reach the 4 and 5, right? So that's why it said that we have node 1 is our permanent. The next node 2 and 3 will be our temporary. Formula, okay. So from this one, okay, we can apply this formula. Okay. Ui plus Dij and I. So our I will be node 1. Okay, so from this 0, we plus 100. Sorry, for node 2. Okay, for node 2, 0 plus 100, comma 1. 1 is node 1. Okay, so it will be 100, comma 1. Okay. We get this 130 from this arc. Okay, from 1 to 2 it's 100, from 1 to 3 is 30. Okay. So we just need to add with 0, 0, so our answer will be 101 and 31. Okay. From the two temporary levels, 101 and 31, node 3 yields the smaller distance, okay, U3 equal to 30. Thus, the status of node 3 is changed to permanent. Okay, at the beginning, okay, node 2 and 3 is just temporary, but once we identify the shortest route, okay, we set the shortest to be our permanent. Okay. So node 1 is permanent, node 3 the next permanent. Okay. Again, for iteration 2, okay, node 4 and 5 can be reached from node 3. Okay, because our node 3 is the next permanent, so we will start with node 3 again. So it said node 4 and 5 can be reached from node 3, and the list of labeled nodes become is this one. 4, 5, okay, temporary, temporary. Okay, let's look into this figure again. So from 3, okay, we can reach the node 4 and node 5. And we have 10 and 16 here. So that's why, okay, from 30, we just write 30, 30, and plus 10 for node 4, plus 60 for node 5. Okay, 3, 3 here is node 3. Okay, so we sum this, we get 43 and 93. Temporary label 43 at node 4 is now permanent. Okay, because this one is the shortest route. So the next table, our 4 will be permanent. So in iteration 3, okay, node 2 and 5 can be reached from node 4. Thus, the list of labeled nodes is updated as this one. Okay, so 2 and 5. If we look back into this one, okay, from node 4 we can reach into node 2 and also node 5. So that's why here, okay, they can highlight this node 2 and also node 5. Okay. But here at node 2, the label 55.4 replaced the temporary label 101 from iteration 1 because it provides a shortest route. Also, in iteration 3, node 5 has two alternative labels with the same distance. Okay, U5 equal to 90, 90 and 90. Okay, temporary label 55.4 at node 2 is now permanent. What it's trying to say is, okay, just now, we have our second node is 101. Okay, 100 and connected with node 1. Okay. Now we change, okay, our node 2, okay, we label as 55.4 because we connect the second node to the fourth node, okay, the node 4. So that's why at node 2, the new label replaced the temporary label 101. Okay, this node 4 replaced the node 1. It has two alternatives. Okay. So for node 5, okay, it has two alternatives. Either it connects between node 5 to node 3 or between node 5 to node 4. These two will have the same length. Okay. So let's look into here again. Okay. From node 5, it can connect into 4 and also it can connect to 3. So when we calculate, okay, to connect between these two, it is just the same. Okay, so if you look into this one, 3 to 4 to 5, okay, 10 plus 50 is 60, and also you can go from 5 to 3 to 5, also 60. Okay, so node 2 is now our permanent. Okay, we can change this temporary into permanent. So from iteration 3, we can get into iteration 4. Only permanently labeled node 3 can be reached from node 2. Hence, node 3 cannot be labeled. The new list of labels remain the same as in iteration 3, except that the label at node 2 now permanent. Okay, this leaves node 5 as the only temporary label. Because node 5 does not lead to other nodes, its labels become permanent and the process end. Okay, so from this table, okay, node 2 now become permanent. But here, node 5 still temporary, right? But we change into permanent because this node 5 does not connect to any other nodes. Okay, no further connection lah. So that's why we change the node 5 into permanent. Okay. Okay, so we will have this sequence. Okay, the desired route will be from 1 to 3 to 4 and to 5, and the total length will be 55 miles. Hmm, so yeah, 1, 3, 1, 3, 4, and 2. Okay, so we get into this bag. Okay, so we get first our node 1. Okay, then the second permanent is 3, the third one is the fourth one, and the last one is node 2. Okay, so if we get back into this figure, okay, from 1 to 3 is 30, then from 3 to 4 is 10. Lastly, from 4 to 2 is 15. If we sum up 30 plus 10 plus 15, the answer will be 55 miles. So this is our shortest route. Okay. Also, the Dijkstra algorithm can be used as this one. Okay. We don't write in table, but we label in a figure like this one. Okay. It is just the same, but here we have the bracket 1, 1, 1 here represent the first iteration. The second, the bracket 2 here represent the second iteration, and the third, the bracket 3 and bracket 3 here represent the iteration 3. Okay, so this is our labeling procedure lah for Dijkstra's algorithm. So for this lecture, for this chapter, we only discuss the minimal spanning tree and shortest route algorithm. Okay. After the class, okay, later you can try to solve some examples in Taha book. Okay, let me show you. Before that, do you have any question? Okay. I'll show you Taha book. Okay, so for this chapter, you can look into chapter 6, network model. You click this one, okay, the bookmark, you click bookmark, okay, so it will show you every chapter in OR book. Okay, you click chapter 6, network models. Okay, So here, okay, we can get all the notes. Okay. For this chapter, you go to exercises. Okay. Okay. So uh, they have problems here, which is the exercise stuff for this book. Okay, you can find the minimum spending free problem and shortest route algorithm, and you can read yourself. Okay, but if you have any problem for these exercises in Faham book, you can ask me at any time. Okay, this class is very short actually. That's why we stop at 3 p.m. Okay. Also, the next class, the game theory also very short. Okay, so you can use that time to do some exercises. Okay, any question? Ada apa-apa pertanyaan? Oh, sebentar. Attendance. Saya keluar dulu ya. Cek. Okay, sekejap. Saya open response. Okay. Saya sudah open respon untuk Google Form, minta isi lecture 12, okay, untuk hari ini. Very silent. Okay. Kalau ada apa-apa pertanyaan tak faham, okay, cubalah tanya ya, sebab network model ni dia akan keluar untuk final dan kamu tidak akan dapat jawab melainkan kamu cuba exercise. Okay. Bukan saja exercise yang dalam tahap tu, dalam lecture note ni sendiri kamu kena cuba buat lah. Okay. Boleh kan?
Boleh doktor.
Okay, nanti saya bagi masa dalam 10 minit macam tu, kamu cuba isi Google Form. Okay, itu sahajalah untuk chapter 7. Okay. Okay, okay, bye-bye.